It is 2026. It's a new season of Advanced Integrated Circuits. And this is an introduction. So what I'm going to do in this short session, well, I don't actually. It might not be short. Let's see. Let's see how much I diverge. Is to go through what I'm going to teach in Advanced Integrated Circuits and give you sort of a highlight. Highlight? Is that the right word? No, probably not. Just give an introduction. First, who am I? Well, my name is Karsten Wolf. I am, well, this is 2026. I'm turning 50 this year. And I've been doing electronics since, I guess I started at NTNU back in, was it 97? Doing electronics. I knew actually a couple of years before that I wanted to study electronics. I thought I was going to do loudspeaker design and wanted to work on audio stuff. That didn't happen, but that was sort of where the passion started. And it really started with opening in a book on electronics and figuring out, it's probably in the shelf behind me. Yeah, I can't see it right now. But opening that book and figuring out that I didn't understand the mathematics. There was stuff in there I didn't know what they meant. I didn't understand the language. And I wanted to understand. So, studied and then started working in, well, okay. I don't consider a PhD actual work. It is a lot of job. It is a lot of work. It is a lot of stress and so on, but it's not really a job. It is a investigation of something that is new. So I did my PhD after the master's, started that in 2003, I guess, 2004. And then finished that PhD in 2008, and then I started actually working. Started in Nordic Semiconductor, where I still am. So I've been with Nordic Semi now for, well, this year it'll be 18 years. 18 years? Yeah, 18 years, I guess. Initially did analog design, ADCs, DC-DCs, some GPIO stuff, whatever needed to be done in order to get the chips out. And then did that for about 7 years. Then I had the bright idea that I wanted to do more. I felt that my own time was not sufficient. I wanted to do more, and I believed that I could do that through other people. So I started as the wireless group manager and led the wireless group for about 7-8 years. And then I figured out that management is really a time hog. It consumes all your time. You don't really have time to do much yourself. You basically focus on helping other people do stuff, which is a good thing, but I sort of missed doing technical things myself. So after a while, I turned back to technical, and in, I guess it was 2023, I moved into a position that we just called IC scientist, which is basically a technical position at Nordic, where I focus on stuff that happens before we go into volume production. It can be quite varied. I also like to teach. It is important for me to try and help others learn what I know, and preferably learn more than I know. Which is why I'm also an associate professor at NTNU, where I teach this course in the spring. So that's me. Been in this industry for a while, done a lot of design, and now teach. So my role in all this is, I like to see it as a guide. I kind of know what cannot be done. That actually is impossible, sort of. Physically impossible, or a bad idea. And I know roughly what's possible. Through working for a while, I have this intuitive sense of, well, okay, that makes sense, that can be done. Or, I don't know. And it's the I don't know, which is interesting, right? Because that's where maybe nobody knows. and we can figure out whether something is actually possible to do and bring the world a slight step forward. And that's really the role, I think, of professors. It is to guide students, to get them to venture into the unknown and find something that is new, that is not known in the scope of or realm of human knowledge, and then make it possible. You don't have to make it polished and make it sort of into a product that you can sell, but you just need to prove that it's possible. As soon as you prove that something is possible, if it is actually valuable, then industry will figure out how to make it easy to do. So PhD students, those are usually the ones that we throw into the unknown and we get them to figure out stuff. Master students, that's you guys usually. What we're trying to do with you is just cram information into your head. And maybe that's the wrong way to say it, actually. We're not trying to put information into your head, because that's really, really hard. We want to ignite a fire in you such that you can figure out stuff on your own. And it's really you that have to sort of teach yourself. But we want you to learn what is possible. We have to bring you up to the line of, this is actually known information. This is easy once you've worked on it for a while. Well, not everything is easy. Quite a lot of things are actually still hard, even after 20 years. But we want you to learn what is possible. Now, bachelor students, that's slightly different, maybe, at least in Norway, where we don't encompass everything. We try to focus the attention on, okay, get to know this particular thing, making PCBs or whatever. Try to figure out how to do that, and then don't go too deep. Don't go all the way down to quantum mechanics. Somebody else is taking care of that. And really, it is industries, so Nordic Semiconductor and others, it is really their job to take what is known to be possible and make it into something that's actually easy to use and can be a benefit to the human race, or to mankind. Is mankind the right word? No, human. to humans living on Earth and beyond, for that matter. So, in this course, I won't teach you everything about life, but I will try to teach you the skills necessary to make your own ICs. And I can't teach you everything there. There's quite a lot of detailed knowledge, but I'll focus in on what I believe to be one of the key things, because the real world is analog. We have concepts like voltage, we have momentum, we have time, which all appear to be relatively continuous values. Now, these continuous values are inherently analog. Doesn't matter if you try to create your abstraction of ones and zeros, it is still analog. And in order to make an integrated circuit, you have to have some analog circuits. You have to have a power supply. You have to have some bias circuits. You have to have clocks. You have to have something that decides what is a 1 and what is a 0. Even memory circuits, where you store your, NAND flash or whatever type of memory circuit you have, you will have analog circuit that reads the value. So the real world is analog, which means there will always be analog circuits, which means there are a certain set of analog circuits that you should know about. Maybe you don't know enough in order to design the details, but you should at least know how roughly they work. And that is the goal in this course. It is to give you like an overview of the type of things, the type of circuits that you will need in order to design your integrated circuits. Somebody else might design a circuit. Let's say you need an oscillator, something to give a clock to your digital circuits. What types of oscillators are there? How do you make them? Right? You don't necessarily have to design them yourself. Or actually, I'm going to force you to design an oscillator, but that's a separate matter. But you do need to know how they work, because you do need to be able to talk to other people that know how to design an oscillator. So we're going to focus on analog circuits because the real world is analog. Now there's a paper, no, article, short story by Peter Kinget on the same type of topic. We are analog. And that means that the things that we'll do in this course will be using analog tools. Analog designers, like myself, we spend years upon years living in our schematics on what you see on the left side here, where we draw, this is a comparator. So let's see if we can find the inputs of this comparator. Well, usually I would call it VI, but here we have the clock that turns the comparator on and off. I suspect that the CI is the actual comparator input. And then we have a latch here. This is a inverter. So this is actually just half the comparator. And these switches are to preset the nodes. And this comparator is actually used in the successive approximation analog to digital converter. And that's what you see on the right side. It is a simulation of a binary search on a SAR ADC. So here, the red and the blue, that's the input voltage. That actually it's the voltage on top of the capacitors on the input of the SAR. So here we store the analog value coming in. You can see it sort of looks like a sine. At some point, we close the switches. Well, open the switches, I guess. We turn them high impedant. And at that point, we do a binary search by adding and subtracting a value to this charge that is not, well, redistributing the charge that is across the capacitors in the SAR. Eventually, we reach a final value where we almost have no differential charge across the differential voltage here. Charge is going to stay the same. And this process of designing a schematic, getting your computer to actually simulate the behavior using the SPICE models that you have inside the computer, and then figuring out, okay, now it seems to work, that is sort of a normal loop of a analog design. Once you have something that you believe is going to work, then starts the physical design, and that is where you actually draw how should the foundry or factory manufacture your circuit. So these two representations, this is the schematic, this is the actual layout, both are needed because it's virtually impossible to read this layout. It's really hard to see, okay, oh, this is obviously comparator. That's not possible. I don't think anybody can do that for rather complex circuits. So we need the schematic in order to inform our brains, what is this thing? How do we actually work with it? And then we need the layout in order to tell the factory how do you want to make the circuit. Because what you're seeing here is a set of transistors on the right side. These are the transistors. The transistor will be in the intersection between the red and the green here. And the same on the other side. I don't actually remember which one are PMOS and NMOS. But that's not that important. We could figure that out. But each one of these intersections, that turns into a transistor. And then we have the drains and sources connected to stuff. So I guess we could identify if we saw... No, we can't really see that because I've cheated. I think these are the PMOSs. And the reason I think that is... You can see a bunch of these AVDDs. That's the digital supply. And those are connected to a lot of PMOSs, while there is only one NMOS that is connected to AVSS. And you can see here that, oh, it's hard for you to see, but I can see there are wires or contacts or connections from the transistor itself all the way up to this metal 4 running across. And you can see that here there's a bunch of connections, and here there's just one. So likely this thing on the right is the PMOSs. But inside this layout, that information is kind of available because each one of the colors actually is a representation of a certain layer on the chip. And that's what is used in order to generate the mask set that the foundry needs in order to develop the circuit. Actually, there was a Veritasium video like yesterday I saw that did a really good description of how circuits are manufactured looking into EUV. I would highly recommend that video. Maybe I should remember to put that in the link below. Let's see if I remember that. So, analog design is kind of designing in a symbolic manner, trying to create a circuit, simulating it, and then you do the actual physical layout, and now you can extract like resistances in this line. You can extract the parasitic capacitance between the blue line that I'm pointing to here and the blue line that I'm pointing to there, and you can see how that affects your circuit. And if you're properly crazy and are doing RF, you might even extract the inductances. But this schematic first, then layout, and then resimulating to make sure that it still works. And then you have to check all the corners. You have to check high voltage, low voltage. You have to check fast PMOSs, fast NMOSs, slow PMOSs, slow NMOSs, and the cross combinations of those. You want to check if you have resistors. You want to make sure you have high resistance, low resistance, high capacitance, low capacitance. All the different corners that you have on your chip. And when I mean by corners, it's kind of like, imagine the multi-dimensional sphere, and that is all the different possibilities for your transistor to end up in. So if you have one axis, for example, for a NMOS, consider that one axis is the threshold voltage, and another axis is the mobility. Now, both the mobility, well, they might be correlated. Mobility and threshold voltage might be somewhat correlated, but in other sense, they might depend on different factors. And now you have variation when you make them, because the threshold voltage just depends on, for example, the doping underneath the bulk, while the mobility depends on the, well, I guess it depends on the curvature of the band structure, isn't that the mobility? No, that's the effective mass, but the effective mass does depend, no, the other way around. The mobility depends on the effective mass, I believe. Mass. So all these factors, all these axes on your single NMOS gives you a sort of a hypersphere or a certain location for where the parameters can end up. Now, that's just for one NMOS. It has a bunch of parameters, like 284 different parameters in the SPICE model. And now you have the same for the PMOSs, and you have the same, not the same, but similar for resistors and capacitors. And when you consider that full matrix of possibilities, there is a certain space in there where it is likely that your design will end up. And you have to check that it works in over those corners. Of course, you can't check everything. So what we normally do is we pick sort of extreme corners and we say, okay, you're not going to find a transistor that is faster than this one. This is the fastest transistor we have. And you're not going to find a slower transistor than this one, NMOS. And then we say, okay, if we simulate those two, and we have the typical, then we're probably good. Or you might do Monte Carlo, or you might do other type of simulation. But that's sort of, we have to make sure that whatever we make is actually solid and can be manufactured in high volume. Now, when we build up a hierarchy of analog design, over the years, I've sort of gotten to a place where I have opinions on how we should design stuff. I've been trying for the last 20 years to simplify how we make analog design. I haven't really succeeded, but I've managed to take a few steps. So I've been working a lot on compiled circuits, so basically taking a programmatic description or a text file description of an analog design and then actually producing the layouts. And that allows me to start simulating the layout before you actually make the schematic. Anyway, what I believe should be done is you should take cells like transistors, like resistors, like capacitors. Those should be standard structures. You shouldn't mess about with the widths and the lengths of transistors too much. Just pick a few and then stick with those, because that makes the layout consistent. And I promise you, it is actually how it is done in the lower nodes. When you go beyond a certain nanometers, below a certain nanometers in a technology, then it'll be standard structures for analog stuff. Because if you have too much flexibility, then it turns out that the variation becomes too large and it's really hard to find a stable design. So I'm going to force you to use standard transistors. You're only going to get a few, and that's we'll get back to that later. Maybe I'll show it today in the tutorial. Once you do a schematic based on standard transistors, actually maybe I had it here. It's too small, you can't see it, but these are actually standard transistors. Once you have that schematic, then the layout ideally should be made by automatic layout. We've been trying to do that for I don't know how many years, 40 years, 50 years, whatever, since we started doing analog design. And it hasn't really worked yet. I don't know why we failed, but I've also tried to do this, and it is really hard. I am not sure it is something that is possible to do with the brains that we have today. What I find is that I can do it, but I struggle with teaching others to do it. So I've made a compiler where you can do this schematic to programmatic layout, and I've been able to do it, and like few of the PhD students I've supervised, they're able to do it. But the broad population of analog designers are not able to do it. I don't know if it's because the typical analog mind doesn't really... It's not well suited to do analog design and to do programming. I don't know. But ideally, I think that our layout should be reproducible and programmatic, because the way it is right now, and you probably will do this also, the layout that you see here is manual. You draw all the lines. Well, actually, the one you're seeing here is programmatic, but the layout that you will draw is manual. As we build our schematics together, at some point we get to a certain complexity where it doesn't make sense to have a schematic anymore. And now we move into the realm of modules and chips. At this point, it should be System Verilog. System Verilog is a hardware description language. It is the one we use in Nordic to describe our chips. It is the language that I think most companies in the world use to describe their digital chips. And that's a good way to describe systems with high complexity. And really, most chips are what we call digital on top. Well, maybe not most chips, but most complex chips are digital on top. You'll find that some of the power management circuits, PMICs for example, the stuff that has your battery chargers and those type of circuits, regulators, things like that, those might be made with analog on top because they are heavily analog and maybe a little bit digital. But most of the complex MCUs, like Nordic chips, like anybody else's microcontrollers, are made with the digital on top strategy, where the top level is actually digital. And then you instantiate the analog in there. So when we look at the full analog or full chip flow, at some point we want to get to what we call the tapeout. That's where we send the final design to the factory and they can manufacture it, and it takes about a year, and then we get it back. Well, depending on how much money you pay, it can be between 2 months and it can be up to a year. If you're a student at your university, you're at the back of the line and your circuit's going to take forever to get through the fab. From the idea though, there's quite a lot of long path from the idea all the way to tape out. Because first we have to describe the system. We do that in XSchem. So that's the schematic editor that we'll be using. Once we have that idea, we kind of know what we want to design. And at this point, we can actually give a idea of the IP. And you're going to design a temperature sensor. I'm going to talk more about that project in a separate video, but you are going to design a temperature sensor. So once you know sort of the top level schematic, you could give that description of the top level schematic to a digital designer, and they could make the digital system that sort of integrates your temperature sensor. And that's where we go into what we call the analog model, or the system Verilog model of the analog. And then we can design the digital design. We can simulate, and this will actually do with iVerilog is a simulator, and actually VPP is a simulator. iVerilog is the compiler, I think. And then we have Verilator, we have GTK Wave to look at the waveforms, or indeed Surfer. And then there is an open lane flow from RTL to GDS, where you can actually translate your digital circuits all the way to a finished layout. Now for the analog flow, we go to simulation in ngSpice, back and forth, fixing the schematic. We go to, well, once we're happy with the schematic simulations, then we make the layout simulation, and now we have to check again. So we actually go back to simulation and we check, is the layout okay? Is the added resistance and capacitance and so on okay? Or do we have to redo the layout? And that is, well, for the temperature sensor, you probably won't have to redo the layout that much. It's probably going to be okay because it's relatively low frequency. But I've experienced for high frequency designs, or indeed other type of layouts, you can go a lot of rounds with the layout. I think the longest I've been privy to is about 12 rounds. We had to do the layout 12 times in order to get it right. Once the layout is done, then we have to check the layout versus schematic. And this is where we check that the schematic that we drew is actually corresponding to the layout. And, well, prosthetics, yeah, those go back to simulation. With that finished layout, we can go to what's called the GDS. GDS is just a file format. I don't remember what it stands for, but it's a stream format, a binary format for how to communicate to the foundry what layer is a certain color, not color, but what is this rectangle that I have right now in my hand? Is it a metal, or is it a contact, or is it a poly, or whatever? That is the GDS. What's commonly done is, once you have the analog, you can integrate that into the digital flow. I actually had a master student a few years ago that did this flow. So she made a few regulators with analog design, and then integrated them into OpenLane. And actually, well, she didn't get it all the way to tapeout, but she made like a top level. That wasn't the point of her master's either, but she made like a top level, top level digital system. Yeah. Okay. So that's the full life flow that we're going to go through. And we're not going to really focus on, in lectures, on how you do stuff in analog schematic and how you do things in layout. That's going to be part of the project. And one thing that would make me really happy, and did make me kind of happy in 2025, is if you, as a student, actually get to a tape out. So I will give you a project. I will give you a task. And maybe then in June this year, you will send a design to manufacturing. So Tiny Tapeout is a company that has for a long time done these open source tapeouts. So for example, actually let's go to, was it B? I think it was this one. Let's see. I think it was this one, wasn't it? Or was it the one, was it A? There we go. Hey. So, in... actually, let me go back once. Oh, crap. Where's the back button? Tiny tapeout chips, and this one closed. Okay, yes, this is the one. Okay, so Tiny Tapeout is a company that buys a certain area from another company, and that company buys. So Chip Foundry is a company that buys bases or wafers at the foundry, which is Skywater. Now, Chip Foundry sells their sort of 10 millimeter piece of silicon to Tiny Tapeout, which is what you see here. This is the full design. And for that 10 millimeter squared design, I think it costs about, let's say, $10,000, roughly. Now, Tiny Tapeout will take that 10 millimeter design and split it up into many, many pieces. I think it's maximum 512 pieces. And then they'll sell each one of those pieces to somebody like me that can tape out a small design. And what we did in 2025 was 2 of the groups that actually made their temperature sensors, which I'll force you to do too, they actually got all the way to a tape out. So here they had a finished design, everything was okay, everything was ready in GitHub. I just had to put it together, put it into one of these Tiny Tapeouts slots, and then get it out there. So yeah, this will probably come back this spring. And you can actually go in here and you can read about those temperature sensors and how they work. And it'll be really interesting to see when they come back, if they start up and if they work. So you can also read, let's see. You can go to, yeah, so here you have the people that actually was part of those groups. So that was really cool. That's really cool to see that students got all the way to tape out. Right, so hopefully you will get there too. I really would like every single one of you to get to the point where you have actually taped out a chip. Now, for 2026, I've gotten Nordic Semiconductor to sponsor the tape outs. So if you actually get to a finished design and something that works that can be taped out, then there's a possibility of taping it out in June 2026. Now, it is not a guarantee though. It is a possibility. So I make all my lecture notes on, well, actually I put them on GitHub and then I compile them and then they're available on this website. So it's analogicus.com, AIC26. There will be a 25, 24, and so on. So I've put in the full lecture notes already, and I've also included a few sort of refresher topics. I'll make, I think I have some old videos, so refresher. There are old videos on refresher, but it's kind of like, it's the stuff that you should have, yeah, that you should have, that you should remember from previous years, but probably don't. So it's about the quantum mechanics, it's about diodes, it's about MOSFETs. It's actually the logic one. That's pretty horrendous. That's just a data dump of all the slide figures I had when I did the course that is called Design of Integrated Circuits. So that's not that useful maybe. But I have something about current sources and so on, the different fundamental components, because I do expect you to actually have some experience with analog design. I expect you to know what the MOSFET is. I expect you to know the equations for a MOSFET. I expect you to know fundamental circuits like current mirrors, like differential pairs, like the amplifiers that we have in integrated circuits. That is, I sort of take that as known knowledge, but maybe it's not. Maybe it isn't known knowledge. I'll try to spend a bit of time in the beginning to just refresh it. And I can't stress enough, it's fantastically important that you tell me exactly what you don't know, and you do it as soon as possible. Because if you tell me early, I can fix it. If you come in May and say, Carsten, I don't understand transistors yet, then you're sort of too late for this course. You're not too late for it in life, but you're too late for this course. But if you tell me like now the 9th of January, when we start up, you can say, okay, you know what? I've never had a single analog course in my life. I don't know up and down on a transistor. then I can sort of, okay, you're in a bit of a tough spot. You're going to have a lot to learn, but I can help you. I can actually sort of say, okay, this is what you just must understand, and I can help you acquire that knowledge. So I really, really, really hope that you will share your lack of knowledge with me. Because if you tell me what you don't know, then I can help you. I know this can be hard. I know some students sort of, I don't know if this is true, but I do think that some students look at sort of what I've done, what my experience is, and then they're sort of afraid of showing me incompetence or whatever. They're afraid that that I consider them to be stupid is not the right word, but they're somehow afraid to talk to me. I think I really want you to don't do that. I'm not a dangerous person. I'm not. You shouldn't be afraid of me. You should ask questions of me. Just believe that I am actually here because I want to help you learn. The reason I teach at NTNU is that Nordic Semiconductor, the company I work for, we need brains. We need brains to understand these topics. And the faster I can teach them to you, the more likely it'll be that you'll come out and you see, okay, maybe Nordic's a fun company to work for, and you come and help us design cool circuits. Circuits that have a real impact on the world. But in order to do that, you have to expose your lack of knowledge to me. Because only then can I help you and direct you in sort of directions of, okay, this is the topic that you need to learn. Or I can get you over the humps that will invariably be there in terms of this I don't understand. I don't understand how the transistor works. Even worse is maybe you've learned stuff that is wrong. So I need you to tell me what you think is correct about transistors so that I can correct it. It's not like I know absolutely everything about transistors. I don't. I forget most of it, which is why I make this video, so I remember what to say next year. But, this is so important. You have to expose your lack of knowledge to me so that I can assist you. So, I put in quite a bit of topics. Story of Jane, that's just for fun. The first thing you should look at is the tutorial. We'll get back to that a bit. And you'll have this introduction. I have to remember they update the video. And I try to put into notes everything that I'm going to say in lectures. So it's kind of like multiple layers of repeating things. I will say things in these videos, and most of the videos I'll be reusing from previous years. Maybe if I feel that when I look at the video I don't like it, I'll make a new one. But everything is available on the website here. You can also download the full book, the lecture notes. So this is, what is it? 450 pages or something. And the lecture notes are not, it's not like a replacement for a book. It is more adding the information that I want you to know. So, yeah. And if you don't want to read the whole book, you can also download the chapters as more like paper formats. So you can read it in chunks. And that's kind of what I would recommend. Before each lecture, it would be nice if you download these and then read through them. Because if you read through the lecture notes before the lecture, then you can ask questions. You can actually have informed opinions on what does this mean, or what do you mean here, or this is wrong. So everything is there. If you're not at NTNU, feel free to send me questions. I have not been overwhelmed by it yet. And just know that I don't respond immediately. I respond when I feel like it. Okay, in order to make integrated circuits, there's so much information you must know, and you cannot do it alone. You have to have a full team. There will be many different skills needed in order to make integrated circuits. Here is just a list of some of them. And even important things like convincing people, or how do you manage stress? That is really important. Even though in the project and in the work that you will do in the next 30, 50 years, there will be a lot of stress, it's good to have some philosophy on how you should do things. To get that sort of internal feeling for, okay, what I'm doing right now, that's stupid. That's not right. That's not correct. I should stop. I should change. I should make it better. I like the Zen of Python. Actually, if you haven't seen that, it's kind of fun. So you go to a terminal, you write Python, and you do import this. And then you get the Zen of Python. And these are pretty good rules to follow. It's things to sort of keep in the back of your mind, that beautiful is better than ugly. And if something is hard to explain, it's probably a bad idea. Because so much of what we do within design of circuits is based on predicting the future. We're trying to predict how a circuit will work in about 1 to 2 years. And in the beginning, it's sort of mostly brain spice. It's brain simulation of the circuit. When you do architecture, for example, system architecture, you are trying to imagine how this whole system is going to function, and you're trying to sort of extrapolate from your brain and knowledge of the circuits. How should the different components work together, roughly? And then there's a lot of work of actually designing it like that. But if you get the initial steps wrong, then it's going to turn out to be horrible. It's like the first topic we'll have in the next lecture is on electrostatic discharge, which is what happens when you touch, well, sometimes happens when you touch a mouse, and why you'll find that the PCB is sort of spaced out, spaced out from the actual edges of the mouse, right? There's a certain distance from all the different cracks here until the PCB, and the PCB's been actually made to tolerate a sap when you walked across a carpet with your wool socks or whatever, or picked up or left some electrons behind, and you touched it and it saps it. Those kind of electrostatic discharge is the type of things that if you don't think about it early enough, you'll get to the end. And if it doesn't pass your ESD test, the work that you've done over the past 2 to 3 years is completely wasted. You can't sell the circuit. So I think it's good to sort of bake in a little bit of philosophy. It's like I've been doing this for a while, and I'll try to say stuff and also go off on tangents and lectures, and just hopefully you'll remember some of it, and maybe you try to then steer clear of some of the bad designs that are in your future, and the disappointments that are in your future, and maybe the disappointments where you worked on a circuit for 2 years and they say, figure out that this is stupid, this will never work. Yeah. Now, a fundamental truth of learning something, I believe, is that you have to, especially when it comes to things like programming, things like analog design, is you have to do it. You have to actually get your hands dirty. You have to feel the pain of my circuit doesn't work and I got no clue why, and you sort of get into that problem solving mentality of taking it step by step and really figuring out. Now, for analog design, you probably don't have a problem that you want to solve yet, but I'm going to give you that. You're going to design a temperature sensor, and you can use analog design in order to do it. What you see on the screen right now is kind of like just me having a bit of fun. If you copy this statement, let's go out to Python, and you run it, you'll find that it'll replace programming with analog design. It's just a fun little Perl regex. Okay, so the analog design process, as we are that I've talked about a bit before, is you have to define the problem. You're going to design a temperature sensor. You're going to find the circuits. You're going to go search on an IEEE Explorer. You're going to find in books. Then at some point, you're going to sit down and you can design the op-amp or you design the circuit, and you're going to figure out the transistor sizes. Here, I'm going to help you a little bit. I'm going to give you a quantized set of transistors. And then you have to write a verification plan. So with my band gap or whatever circuit you're going to make, what should I verify? Let's say you're making an op-amp. Now you have no friggin' idea. Maybe. Maybe you do. I don't know. You might not have an idea of what you should simulate on your op-amp. But turns out these days we have chat, and it's actually not that bad. So write a verification plan for an OTA, so operational transconductance amplifier, focusing on issues that could occur in a band gap design for integrated circuits. The technology is Sky 130 water 130 nanometer. Let's see what it says. So it's a good way to start integrating LLMs into your system. And it is actually a very good way of learning something new, I think. You always have to check it, right? And you have to read it and have an internal dialogue with yourself, and is this true or not? But usually it gets it relatively well. So here it starts describing what's important in the band gap. Band gap you don't know yet, but I'll teach you about that. And that is one of the circuits that you will need in your oscillator. So it goes through, challenges, little headroom, and then let's see where if you get to verification. Yeah. Oh, that was long. I don't want to read the whole thing. Okay, so startup. This is important that it actually starts. And here you can see also it proposes corners. So what you have to check at fast, hot, and so on. These are really good items. So I would also encourage you to use chat as part of your design in order to sort of guide you into what do I need to simulate. I should probably check this list. This is really good. Okay. So you're checking your design. You're checking everything that chat has told you to do or not. You have to decide yourself whether it's important. You do the layout, and then you check again a few things, maybe not everything. And if it fails, you go back and you do it again. So my goal is to really teach you. It's to guide you. I consider myself a mountain guide. I consider myself a person that can show you the mountain and show you the paths up the mountain, but you really have to be the climber. You have to do all the work yourself. You are the one that has to have to teach yourself everything. I can try and guide you so that you don't completely break down and fall off the mountain and die, but other than that, you're in for a lot of work. So I consider my role as enabling you to read the books, to read the papers, and to help you correct misunderstandings. So we'll start this in 9th of January in R90 at 8:15, and the lectures will be Friday at 8:15, and then we'll do that for about a couple hours. Then we'll actually take a break and we'll walk over to another room. I think this is Kjell Fida. And there we'll sit together and we do the project hours. And I'll help you through the project. So actually, let me have a look at, let me show you the lecture plan so we can see what we're gonna do. Yes. So this is the lecture plan. Usually I stick to the lecture plan quite religiously. Hopefully there's no changes this year. Let's see. But first is the introduction. I'll also introduce the project in the project out here, but here it's refreshing. A couple of weeks of refreshing topics, really going through from all the way from quantum mechanics to transistors, how they work, and trying to help you refresh what you should already know. And then we'll go into integrated circuits. How are they at the top level? How does electrostatic discharge work? What's the quantum mechanical fun by GG NMOS or grounded gate NMOSes or latch up and those kind of type of phenomena? Then we'll do references and biases. This is integral to the project. Lecture 4, that, well, yeah, I call this lecture 4. It's on filters, active RC and GMC, and also on digital to analog converters. They will do switch capacitor circuits, which are essential for, well, back in the day, discrete time filters and sigma delta modulators and integrators and analog to digital converters. We'll do oversampling sigma delta or oversampling analog to digital converters. We'll do low dropout regulators. We'll do ultra low power type of stuff. We'll do buck and boost. So that is DC-DC regulators going up and down in voltage. We'll do different types of control schemes for those type of circuits. We'll drift into phase lock loops and voltage-controlled oscillators, frequency detectors, loop filters, dividers, and so on. There'll be topics on RC oscillators. Actually, the oscillator that you're going to design as part of the project is an RC oscillator, a temperature-dependent RC oscillator. And then it's more like information topics on how does radios work and energy harvesting. And then at the end, we're going to talk about, okay, now you know quite a bit about analog circuits. How do you integrate them into larger systems using system Verilog models? Now, these are the lectures, but really most of the load on you as a person in this course is the project. It is these milestones. And I'll do a separate video on the project. Let's see, where are we now? Yes, there is a playlist on YouTube where I've put in, let me put those at the bottom, where I've put in the previous year's, no, that didn't work. Lecture notes. So here you'll find refresher. I might make those again. Let's see. I didn't like them when I listened to them this year. I put in a new tutorial and MOSFET and so on. So you can find all the lectures here. And what I usually do to remind myself what I'm going to say in the lecture is actually watch the video before the lecture. And then if I don't like it, I might remake it. But usually that's how I remember what I'm going to say in the lecture. So if you watch the video before the lecture, that's an advantage, because if there's something you don't understand, well, ask me in the lectures and we can sort of dig deep on that topic. I'd love that. So the best thing in lectures is if I get questions and we sort of spend really a long time on nailing that particular question so that everybody in the room understands it. It's much better to spend a lot of time on understanding a little bit than just glossing over everything. And I promise you, this course is primarily a glossing over everything type of course. It's like, let's take PLLs, right? I know people that spend their life on PLLs. That's all they do. So every single one of these lectures, you can do a PhD on the topic. So we're not going to do that, but yeah, please ask questions in the lectures. It makes it so much more engaging for everybody, I think. So we have the analog integrated circuit design. There it is. This one. This is the book. You need to have the book. Yeah, so it's maybe you have it already from Analog CMOS. And we're gonna use, well, if you come to the lectures and if you read the book and if you ask me questions about things that you don't understand in the book, then I think you're gonna learn a lot. So this book is excellent. Oh, that didn't really show up, but it's an excellent book on analog design. I really would recommend that you buy it and read it. So exam, I have no idea when it's going to be, but it counts for 55% of the grade. There is a compulsory exercise. It's actually kind of part of the project, but this you have to start now. You have to start immediately. And maybe, as you saw from the how do we go back? From the lecture notes, if we go to the plan, you can see, sorry, in week 4, there is milestone 0. This is actually a deliverable on Blackboard, so it'll be like a milestone there. You have to actually do it in order to get the best grade possible on a project. This milestone counts towards your grade. So that milestone is going through the tutorial. Now this is a lot of work. It's not a big design, but it is a lot of work, because what you have to do is you have to install the tools. I expect you to install the tools on your computer. So you have to install ngSpice, NetGen, XGAM, and so on. You should have all these tools installed, and then you'll be able to do the tutorial. Now, even though I say that you're a student of mine, you have to install the tools, you have to get it working locally, then some of you won't do it. So it is possible to do without also. You can use the Docker image. So there is a Docker image, and if you're lucky, then you might be able to use that to do the tutorial. If you watch the video, you can see me starting in the Docker image, and then about halfway I'll switch to actually doing in the native build tools, because it's so frigging slow. So I mentioned that I'll force you to use a couple of transistors. And what you can see, let's see if we can. All right, yeah. So this is the fantastically advanced design that you'll make on the tutorial. It's basically a current mirror. But notice something here. These have a certain name, these transistors. So it's Janeway analog transistor underscore NCH NMOS underscore 4 contacts. So that's determines the width of the transistor. And 5F0, that says, okay, it's roughly 5 times the minimum gate length. And this is sort of like a standard component. I want you to use these type of transistors because as you're starting out, if you have full flexibility of the width and the length of the transistor, you'll get lost. You'll get lost in the forest. So just use these and you'll get it roughly correct. As you know more and as you learn more, you can have more freedom. But in the beginning now, I do think it's good for you to have less freedom. So the good thing about using these transistors is, you'll see that in the video, I can help you a bit with the layout. This is the layout of the transistors, because the layout is actually done already, and then it makes it easier to do the layout if you use these transistors. Okay, so start with the tutorial as soon as you can. The project counts for 45% of the grade, and you can't do the exam without having done the project. So if you don't hand in the project, you will not be able to do the exam. Very important. And the project is not easy. It is relatively hard. So we'll use the open source tools, which means that you don't have to sign any non-disclosure agreements. You don't have to do anything on that. You just have to download it, get it working, and then do the tutorial. And there's also something called AIC26, where I have the collection of, well, the type of IPs that you could need. So for example, the analog transistor library. Let's have a look at that. These are the different transistors that you have access to. And let's see. So these are two different type of transistors. One that is relatively short. So this is called 1F2. And one that is longer, 5F0. So 5F0 is good for current mirrors. 1F2 is good for cascodes and differential pairs. And you can go in here and you can say, well, which one did we have for the current mirror? Let's have a look. So here we had 4C5F0. So 4C5F0. We can go in and we can also see, okay, at what type of GMID, or at a GMI over ID of 10, which is moderate to strong inversion, how much current do I need to put into the transistor? Or at a GMID of 15, which is closer to subthreshold, how much current do I need to put in? And what is the VGS? So you can actually go in and read those out directly. And then you can also look at, let's see, the 1F, you can see that the same width, but different length. You can see that the current is also different. Huh? Yeah, that's right. Yeah. We wanted the NCH. Yeah, so you can see 18 microamps for 15, and you need 5 microamps for the longer length. That makes sense, right? So you can go into these tables and you can read out directly what the properties of your transistor is. That's useful when you start at the design. There's also a tutorial on how do you combine System Verilog with analog design, so you can actually co-simulate System Verilog or a single System Verilog file and your SPICE design. There is the previous years. So here we have the two groups that actually made it all the way to a tapeout last year. So you have the full description of their circuit. Now, it's worth a read. I wouldn't necessarily recommend doing exactly their design. I would try to make it better. And one thing that is good to know is that this year I've made a temperature sensor where I haven't made the layout yet, but it's a full design in here. So it actually describes a full design on what I expect you guys to make. You don't have to do the same thing, but this can be used as a guide to see, okay, how did he do that? How did he actually simulate this and so on? So useful to use that AIC26. And it also gives you the framework for how to run the simulations and so on. So yeah, you'll get to know AIC26 through the tutorial. And by the way, each one of the seasons, so 2022, that was named after Aaron Sun and Farscape. 2023, Ellen Ripley. 2024, that was named after Sarah Connor. And then we have Catherine Janeway in 2025. Now 2026, that's named after Lilu and Fifth Element. Because, well, I like sci-fi. And I like strong women in sci-fi. Anyway. So, we're going to use EDA software. Also, electronic design assistant software. Now, it's not great. It is relatively... well, the open source tools are great because you can modify them if you don't like them. But don't expect the software to be polished. Don't expect that it's Visual Studio. You'll spend a lot of time in this course. Actually, I want to end with a quote. So I'll do a video about the project also, but let's jump to I asked students from last year if they can give me a quote about the project, and I got 2. So, Advanced Integrated Circuits is likely one of the most rewarding courses I've attended at NTNU. It gave me a lot of valuable knowledge on different types of circuits, IC dynamic workflows, open source EDA tools I greatly appreciate. It's also one of the most challenging courses due to the amount of time and effort I had to spend to figure things out. Right? Fantastic project course that might turn your world just upside down, push you to reevaluate your life choices and stare briefly into existential void, all while being deeply enjoyable and engaging. So I'm asking a lot of you in this course. But know that I'm doing it because I want to put you into an environment where you actually learn. You've actually gonna learn something. But it requires effort. So it's not for free. So, yeah, I really like those quotes. Great. I hope you have fun in the course. I will try to have fun. I hope you will see that I enjoy communicating electronic design to you. And hopefully we'll have some fun together. So, I'll see you in a couple of weeks, or actually in 1 week. And let's get started. Have a great day.